Alright, today class we're going to talk about a probability density function problem. So, and these are very similar. This particular one is called the distribution is called the exponential distribution. It's actually used in the real world to figure out what call wait times are. So, it's got an actual application. Alright, so here's the deal. First off, we want to consider the function f of x equals k e to the minus 0.2x for x bigger than or equal to 0, and 0 for x less than 0. So this is a piecewise function. Alright, part A. What value of k makes f a probability density function? Part B is going to be what is the median of the probability density function, and part C is going to be what is the mean of the probability density function. Alright, so let's get started. So first off, for part A, the definition of a probability density function is that the integral from negative infinity to infinity of f of x dx is equal to 1. Alright, now in our case, for negative infinity to 0, the value of the function is 0. The integral of 0 is 0. So we're going to just go from 0 to infinity, which is kind of nice. Alright, so we're going to calculate the integral from 0 to infinity of k e to the negative 0.2x dx. Okay, and we're going to set that equal to 1 and solve for k. We're going to integrate this first, though. So this means this is an improper integral, so you're going to have to do the limiting process. So I'm going to let the integral from, as b goes to infinity, of the integral from 0 to b of k e to the negative 0.2x dx. Okay, so now that I made it a proper integral, we'll find the antiderivative for this. And the antiderivative for e to the ax is e to the ax over a. And it's the opposite of differentiation. In differentiation, you multiply by a. So in integration, you divide by a. So that means we're looking at the limit as b goes to infinity of k over negative 0.2 e to the negative 0.2x, and we should evaluate that from 0 to b. So when we plug in our numbers first, and then we'll do our limit. So this would be the limit as b goes to infinity, and let's see, so that's going to be k, or let's make the negative in the top, so k over 0.2 e to the negative 0.2b, that's the only place we see an x, so that's where b goes, and then we'd say minus the negative of whatever when we plug in 0, well that's two minuses, so we're going to say plus, and when I plug 0 into to this, I'm just going to get e to the 0, which is 1. So that's going to be k over 0.2. Alright, so one more step to evaluate the limit. So when we evaluate the limit as b goes to infinity, the only b here I see in the entire problem is right there. That's exponential decay as well, so it's going to go to 0. So this part's just going to go away. And that means we're just going to have this part. So we're going to have our value for this integral is k over 0.2, and that's equal to 1 if it's a probability density function. So this implies that k equals 0.2. Yay, we got part A done. Alright, part B. Part B, it says we want to know what is the median of the probability density function. So we'll start up here. So for part B, the definition of the median, it's the value of m such the integral from negative infinity of f of x dx. This should be the same thing as the integral from m to infinity of f of x dx. Those should both equal 1/2. So exactly 1/2 of the area is on either side of this value of m. Alright, so let's be smart about this. So we know negative infinity to 0, our function 0. So we're going to go with this integral instead of that one, because this is going to be a finite integral. We're not going to have any improper integration. So this would be, for us, the integral from 0 to m of our probability density function, which is 0.2 e to the negative 0.2x dx. Okay, so that's the integral we're going to compute, and we already just did the antiderivative a second ago, so we know we divide by negative 0.2. So this is going to be 0.2 over negative 0.2 e to the minus 0.2x evaluated from 0 to m. Okay, and once again, this is kind of convenient. So the 0.2's are going to cancel. We're going to have a negative e to the minus 0.2m. Okay, and when I plug in 0, I'm going to get 1. So it's going to end up being plus 1, because once again, the 0.2's cancel. And that's supposed to be equal to 1/2. Alright, so I want to solve for m. So this is our standard sort of exponential equation. So we're going to move the 1/2 over, and you're going to have a negative on both sides, so we'll cancel those negatives off. So we'll move the 1 over and cancel the negatives at the same time. So this would mean we have e to the negative 0.2m equals 1/2. Alright, and we're going to take the log of both sides, right? So the log of this side is going to be negative 0.2m. And then we've got that equal to the log of 1/2. Alright, and the nice thing about log of 1/2, that's log of 1 minus log of 2, and log of 1 0. And the negatives, once again, the negative here and the negative over there are going to end up canceling. So m is going to be 1 over 0.2 natural log of 2, and 1 over 0.2 is 5. So let's go ahead and say 5 natural log of 2. Alright, so half of the people who are, so this is a phone thing and you're trying to figure out the wait time, half of the people are going to have to wait this long, which, I don't know, 5 times 1.4, whatever that is, approximately, this long, and the other half of the people are going to have to wait more than that. Alright, so let's do Part C. We're asked for what is the mean of the PDF. So let me get a new sheet of paper for that. Alright. So for the mean, Part C here. Okay, so for the mean, this is going to be the integral from negative infinity to infinity of x, f of x dx. Okay, mean here, same as average. Makes, you know, the old saying, average people are mean, right? For us, once again, this is going to be the integral from 0 to infinity of x. I'm going to put my 0.2 out front here. So 0.2x e to the negative 0.2x dx. Okay. Good news is this one's not too hard. Bad news is it's integration by parts. So I'm going to do this by tabular integration. Alright, so tabular integration says the u is going to be the 0.2x and the dv is going to be e to the negative 0.2x. Alright, we take derivatives on this column, and then we take integrals on this column to match. So we're going to have minus e to the negative 0.2x over 0.2 and e to the minus 0.2x over 0.2 squared. I'm going to write it like that, and you'll see why in a second. Okay? So we multiply this one times that one, and multiply by positive, and this times that one, and change its sign. Alright. Alright, so we're gonna make this we're gonna make this a proper integral first. So its limit as b goes to infinity from 0 to b of 0.2x e to the minus 0.2x dx. And now I know my antiderivative, so this is the limit as b approaches infinity of, let's see, so it's this times this one. So all these are going to end up being negative. Now notice the 0.2 and the 0.2 are going to cancel, so it's going to be minus x e to the negative 0.2x. Okay? And then this one's also going to be negative because of that minus sign. So 0.2 over 0.2 squared is going to just be over 0.2. So this is also going to be negative 1 over 0.2 e to the minus 0.2x, and that's evaluated from 0 to b. Okay, so let's plug the things in, and then we'll evaluate our limit. We'll be done. All right, so we plug b in, we're going to get negative b e to the negative 0.2b minus 1 over 0.2 e to the negative 0.2b. And when we plug 0 into the x e to the whatever, that's 0 times whatever, right? So that's going to be 0. And when we plug 0 into this one, it's going to end up being plus, because we're subtracting again, 1 over 0.2. Okay, now we know polynomials and exponentials. We know that polynomials are weaker, much weaker. So whatever happens to the exponential is going to happen to everything. So this is going to go to 0. And you could, if you don't believe me, you could do L'Hopital's rule. This could go to 0. So our answer is going to be 1 over 0.2, or 5. So if this were the probability density function for a phone company making, with you calling in to get some kind of help, the average waiting time would be 5 minutes. Which, I don't know, maybe not too long. Maybe kind of long. All right, doodles.